Welcome back, folks, to another exciting JLAM Bio video. Today, our focus in integrated chemistry physics. We're switching it up a little bit. We're talking about waves. We're going to focus on the nature of waves and wave properties. And you probably don't realize how important waves really are to our day-to-day lives. The fact that you're actually hearing this is due to the fact that the speakers on whatever device you're looking at are producing a sound wave, and it is traveling through the air into your ear, and your brain is able to process that particular information so that you can understand what I'm saying. So really interesting to take a look at this in a little bit closer level. We'll then expand on this as we start looking into units that are focused on sound and other waves. Yeah. By the way, this video is brought to you by Big K Diet Cola. Not a sponsor. Big K Diet Cola. All the great taste with no calories. Big K Diet Cola. Oh, that's refreshing. So hopefully by the end of this video, you should be able to understand and explain how waves transfer energy, differentiate between longitudinal waves and transverse waves, and explain different parts of a wave and the relationship between frequency and wavelength. So let's talk a little bit about waves and what they are. Waves are just a repeating disturbance that transfers energy through matter or space. I'd like you to think about a falling pebble in a pond of water. When that pebble falls, you remember from our previous units that it contains energy, and that energy is transferred to the water when the pebble actually hits the water itself. Now, the response to that energy that is being absorbed by the water is to produce a wave, and that's why you see in the picture there, when you drop a pebble in a pond of water, you get a wave pattern, and that wave continues to flow through the entire water, slowly dissipating, but you continually see that wave move across the water. Think about a rope or a slinky. Again, not a sponsor, but the rope exercise where you've seen it all in like the Rocky movies and things like that, where they have the montage of the weak guy that like starts working out a whole lot, and he takes the ropes and he starts moving them up and down really fast. Well, the energy that's being used by that man is being transferred into the ropes. And as you see, the rope kind of has a peak and a valley as you go through and continue to move it up and down, slowly dissipating as it goes across. So lots of different ways that we can look at waves, but those are just a couple of easy examples to think about. Now, there are a couple different types of waves that we are going to talk about. The first one is a mechanical wave, and these are waves that can travel only through matter. Medium is the substance that the matter is traveling through. So, for example, when the person in the picture touches the water is the medium itself, and how fast waves travel and the frequency and the wavelength is directly related to the medium that it is moving through, as well as the amount of energy that particular wave has. Now, transverse waves are waves that travel at a right angle to the direction that the wave travels. So, for example, here you have a very stormy ocean, right? And the wave is moving across the ocean itself, but the wave itself moves up and down at a 90-degree angle. It goes up and down, essentially perpendicular to the ocean itself. So while the wave travels from left to right across the ocean, the wave itself goes up and down. Now, this is opposite that of longitudinal waves, and longitudinal waves travel the same direction that the wave travels. So, for example, sound waves are a good example of this. And an example of a longitudinal wave would be a spring. You can expand the spring, and then when you let go, you can actually see the wave moving back and forth. Again, you also see this in a slinky. If you hold a slinky and stretch it out a little bit, and then you pull back on one of the little metal pieces and let it go, you can actually see the wave move through the slinky. You see areas of compression and you see areas of expansion. Now, an example of this is a sound wave. Sound waves travel like this. And again, sound waves are also mechanical waves, so it requires a medium to travel through. You've probably heard the old adage that nobody in space can hear you scream. And that's technically true, because in space, there is no air. It is just a vacuum. There is no matter in deep space. And so if you were to try to talk, you wouldn't actually produce a sound. Interestingly enough, astronauts, if they're out in space, in order to communicate, they're trained that if their electromagnetic walkie-talkie type device goes out, that they can actually, if their helmets are actually touching each other, then that actually creates a way for the wave to be able to travel through the helmet so that the other person can hear. It's kind of like the old tin cans on a string. that the person holding the one can talk into it, and then the vibrations along the string will actually go out the other can so that you can hear it. So let's talk about some properties of a wave. Transverse waves have crests and troughs, which is what you see on the right-hand side there, crest being the peak and trough being the lower part. Now, longitudinal waves have areas of compression, which is where the slinky would be very close together, and rarefaction, where the pieces of slinky would be far apart. So a couple of other key vocabulary terms here that we need to focus on is wavelength and frequency. Wavelength is the distance between one point in a wave and the nearest point just like it. So basically, peak to peak or trough to trough would equal a wavelength, and we can measure that in meters. Frequency is the number of wavelengths that occur per second. So if you could imagine one of those particular graphs has lots more waves, lots more peaks and troughs in it, then the frequency of that particular wave would be greater than the original. Frequency is measured in hertz. And period is the amount of time it takes for one wavelength to pass a particular point. So wavelength and period are very, very similar. It's just that with period, we're focusing on the time it takes for basically one wavelength to move past a certain point. So wavelength is related to frequency, and we have a formula for this where the speed of the wave itself in meters per second is equal to the frequency measured in hertz multiplied by the wavelength measured in meters. So as you can see here, we can do some pretty simple calculations with this. What is the speed of a sound wave that has a wavelength of 2 meters and a frequency of 170.5 hertz? Well, we go back and think about our formula where the speed, we'll call it velocity, is equal to the wavelength. That's given by lambda, just so you know. It's just the way we look at wavelength. Multiplied by the frequency, f. And so we just plug in our numbers and solve. Velocity equals 2.00 meters multiplied by 170.5 hertz. Plug into your calculator and get your answer. What we get is 341 meters per second. Okay. So again, just pretty easy to go in, plug in, and solve and get some of these answers. Really, really easy. All right, let's move on. And by move on, I mean close out this video, very simple wave video for today. So hopefully by the end of this video, you can do all of these student learning objectives. Once again, I really appreciate you guys watching these videos, taking the time out of your day. Make sure you let me know if you have any questions, and we will see you guys next time. Have a great day, guys. We will talk to you later. Bye-bye.